design. Users can download applications from different sources, including both official and third-party, which makes keeping control over malwares increasingly challenging. Current analysis tools can be mainly divided into two parts. That is static analysis and dynamic analysis. The static analysis solution mainly focuses on reverse engineering the .apk package and recovering the source, further analyzing on the recovered codes by symbolic execution or other analysis methods like tinted follow analysis. To some extent, it's similar to asking the computer to review the code for us. The method doesn't need to execute the application and can't check the vulnerabilities during the running time. On the other hand, malware authors can bypass analysis by dynamic library loading, like loading the library during the running time and the code application. In other words, exchange the codes to the ones that are equivalent with respect to functions or how to understand, which are commonly used technologies enabled by developers to protect the source code of the application. To the dynamic solution, the target will execute in a controlled environment to generate a behavioral footprint, which will further analyzed. However, as more interfaces and sensors appear on the mobile phone, it becomes harder to simulate a real mobile phone with the virtual machine. Then turn to security issue my project aims to solve. Due to the internal storage limitation, the developer tends to save some relatively non-sensitive data to the SD cards, although explained to be non-sensitive individually. The non-sensitive data can upgrade to be sensitive when combined with other data or the public available information and can be accessible by all the applications installed. Since they are allocated on the public storage space, the picture above is just an simple example. As we can see, even image can leak privacy. The objective of my project is to develop an analysis tool that can detect such a security issue by using a real mobile phone as control environment for the dynamic access. In fact, I will choose to monitor the system calls generated by the target applications so that the code application and dynamic library loading can bypass analysis. So the first issue is how can we identify the data stored improperly? Let's return to this initial point. Why does SD card exist in the mobile phones? In my opinion, there are two reasons. The first one, as I have mentioned above, to make up for the insufficient internal storage space, while the second one is for data sharing between applications. There are several well-known directories in the SD card for this purpose, as you can see in the table here. In fact, we can't handle the second type of storage, so we choose to bypass it. However, we can handle the first one easily by filtering the file operation path out of the system call and give alarm once the storage directory is not the one in the table, and forward to the server. Next. The next issue is how to simulate user operation during the running time. By reviewing several existing dynamic analysis tools, I found that a common line tool called Monkey in ADB model is commonly used, which can guarantee random user events. For example, the AA sandbox uses 500 monkey events to simulate the user input. At the beginning, I plan to write the tool by myself. Then, after reviewing a paper from this department, I found an existing library function in the Linux system that can monitor the process, even the child process generated by fork function. Given the fact that the Android platform is based on the same kernel, I can further port the trace function to the Android operating system. Fortunately, when I tested on the emulator of Android 6.0, I found that the function had already been installed. Then I test the function according to the following flowchart. As you can see in my final result, the complete file storage directory has been able to be extracted from the system call completely. But at this point, I'm unable to point whether our application is problematic or not when not consider the detailed location of the problem. So my supervisor gave me some suggestion that I can review the code by myself. And after reviewing the source code of streets function, I found that in the latest 4.10 version of streets function, or even the previous one, 4.9, one more option called -k has been set up, and we can trace the complete stack trace by such a function. However, one additional library is needed. So first, I installed the required function on the Linux operating system first and test on it, and I can get the complete stack trace between the system just as expected. And in the next step, I need to write one real mobile phone for experiment, install the required library to open the stack trace option, close compile a straight ARM version for the Android, and finally install at rotate phone. Beyond that, I will write an analysis program to encapsulate the whole process so that my tool can generate some hints to the other group. We mainly focus on static analysis and correcting the error by reverse engineering on the intermediate code, like the name of the public API that causes security issue, which is the main job I need to do in the next semester.